Hello all, welcome back to operating system course. So in the last class we had started the third chapter, synchronization and deadlocks. So we had discussed about synchronization, right? What is synchronization, what is producer consumer problem, and we had also seen about the race condition. So today we'll get started with the next topic in synchronization itself, which is the critical section management. So before that we'll understand what is a critical section, then we'll see how can we manage that one. Okay. Now a critical section, it can be defined as a part of a program where the shared memory can be accessed. Okay, so say suppose your system contains n processes like P0, P1, P2 up to Pn minus 1. So each of those process will have this critical section. Okay, so this is a generic structure. This whatever you can see in the diagram, right? This is the generic structure of a process. Every process will have these sections like entry section, critical section, exit, and then the reminder section. So first we'll talk about the critical section. So it is a part of code, okay, wherein the shared memory can be accessed. So this critical section, it is present in each processes, and that portion or that code segment can be shared between different processes. Okay, like in this particular critical section, your process, it may be using some shared variable. It might be updating in the shared variable. It might be writing something into the table, updating files, or it is accessing IO devices, something like that. That shared memory content, it would be present in the critical section. So this critical section, it can be shared between multiple processes. Fine. So first now we'll see about the entry section. Okay, before that we have to understand one thing here. So whenever a process is executing in its critical section, that means say a process P1, it is executing critical section means P1 is using the shared memory. It is updating something into the shared memory. At that particular time, no other process should be there in the critical section, or no process apart from your P1 should be allowed to access this critical section. So always at any point of time, only one process should be given the access for this critical section. Okay. Then we'll talk about the entry section. So whenever a process say it wants to execute in its critical section, so first a request has to be sent, or a discussion has to be made among multiple processes. Say suppose in our process we have five in our system we have five process, and all these five process are waiting for this critical section, or waiting for entering into the critical section. At this time what will happen is like they cannot randomly go and execute this critical section. A discussion has to be made among these five processes, so that among them one process would be chosen and it is allowed to enter the critical section. So the entry section is that part of the code wherein it has the actual code for the request that is made by the process. So the okay, so each process that must request, it must request permission to enter its critical section. Now this entry section, it is that part of the code which implements the request to the critical section. Okay, so this entry section, it is followed by the critical section. We have already seen what is this. Then this critical section is followed by the exit section. So this exit is nothing but, say suppose your process P1 is executing this shared memory, like it is doing some work in the shared memory or the critical section. Once it has done its accessing of the shared memory, or once it has been done with this critical section, it will exit from that particular section. So that exit, we call it as the code for that is present in the exit section. The exit section is followed by then the reminder section. So this is nothing but the remaining code of that particular process. Like once it is done with the critical section, it has some other instructions to be executed that would be present in this reminder section. So in the last class we had seen about the producer consumer problem, right? So there we were accessing a count variable. So in the producer process, count was incrementing by 1, and in the consumer process, count was decrementing by 1. So we had seen that count variable is a shared variable, right, between your producer and the consumer process. Now that count variable is nothing but your critical section. Okay. So, as we had seen in the critical section, only one process would be allowed to be in its critical section. So, multiple processes at the same time cannot access this critical section. We had seen this in the producer-consumer problem as well. So, if the producer it tries to access the count variable, then the consumer should not access it, correct? So, and the vice versa. When consumer process is using the count variable, the producer process should not access it. So that means the access to this critical section, it must be mutual exclusive. Exclusive in the sense only one process has to access this critical section. So if multiple process access this critical section at the same time, then what will happen is your data inconsistency will occur. So again, we had seen this data inconsistency in the last video, right? Wherein, the producer process and the consumer process, we had seen that, and we had taken one example. Let me show you that slide. This one, right? Wherein we were about to get the count value as 5, but we were getting 6 and 4. So we had termed this as race condition, right? So whenever two or more process, it will access the critical section at the same time, then what will happen? Then you have the data inconsistency problem. So now this critical section, it is used to design protocols which ensures that the race condition will never occur. Again, race condition when it will occur? When you have the data inconsistency. So whenever you have this critical section management, so you can make sure that your race condition will never occur. Then how to solve this critical section, right? So there are two ways. One is one you have the hardware solution for solving the critical section problem. Another one is the software solution. In the hardware solution, you have synchronization hardware to solve this, and if you take the software solution, you have Peterson solutions. So these things are there not there in your syllabus, so we'll not go into the detail of that. So whenever any solution is used for this critical section problem to solve, so maybe it is Peterson solution or synchronization hardware, anything we take, those things or those solution, it needs to satisfy three requirements. Okay, the solution to your critical section problem, it needs to satisfy three main requirements. So those three requirements are mutual exclusion, progress, and bounded waiting. So we'll see these things now one by one. So first one is mutual exclusion. This we have already seen. That means whenever one process it is executing in its critical section, then the other process should wait, or else we say that the other process should not be given a chance to execute in that critical section. Say suppose we have process P1 which is executing in its critical section, then we have to make sure the other processes like P2, P3, whatever the processes are there, they should not execute in their critical section. Okay, so this is your mutual exclusion. That means at the same time, no multiple process should be executing in their critical section. The second one is progress. Okay, so say suppose our critical section is empty. Empty in the sense no process, none of the process are executing in the critical section. That means critical section is empty. Say um, there are some processes like P0, P1, a set of process we will consider. So they are wishing to enter the critical section. Okay, so we had given a condition for this progress as your, I'll write here, your critical section, it is empty. Okay, and we have a set of processes P1, P2, something like this. So these processes are waiting for the waiting to enter their critical section. Now the decision about which process should be allowed to enter the critical section, it should be decided within a frame or within some finite amount of time. And again, who will decide it? So only those processes which are not executing in their reminder section, they can participate in this discussion and they can choose a process. I'll go back to the diagram. I'll explain here. Okay. So say suppose this critical section is empty. No processes are executing here, and we have some processes P1, P2, P3, P4. Okay. Let's consider there are 4 processes in the system, and now these 4 processes are wishing to enter this critical section, or they want to execute this critical section. Now who will be allowed to enter the critical section would be decided by this process. How it would be decided? Now say suppose these 3 processes, they are not executing anything. Okay, they are simply there in the system, and P4, say suppose previously it was there in the critical section and now it is executing the reminder section. It has executed critical section, then it exited from it, and now it is currently in its reminder section. Now only process P1, P2, P3 can enter into the discussion, or only these 3 processes within some given time, they have to decide who will enter the critical section. In this discussion, P4 should not be allowed. Why? Because it is currently executing some of the instructions, right? It is busy. P4 is busy, so it is not allowed in the discussion. Only the discussion is between the P1, P2, P3 process, and among them, one is chosen to enter this critical section. So that is the progress. Then the third requirement is bounded waiting. So bounded waiting is nothing but, bound means a limit. Okay, so there should be a limit on the number of times that the process are allowed to enter the critical section. So after a process has made a request to enter its critical section, and before that request is granted, there should be a limit on the number of times it must be allowed. So a process cannot be given simply multiple times to enter the critical section and execute it. Why? Because we have multiple process in the system, and all the process should be given fair chance to execute in that critical section. So this is about your critical section and its management, the requirements and all. Next we will see about semaphores. So this semaphore, it is an integer variable and it is shared between the threads. Okay, so this variable we usually denote semaphore as s. Okay, so this variable, this semaphore, this s variable, it is used to solve your critical section problem and to achieve synchronization in the multiprocessing environment. So here it is that, right, to overcome the synchronization problem. So you can you can initialize this semaphore to a integer value. Apart from that initialization, you can only access this variable through 2 operations. Okay, so there are only 2 atomic operations which can be performed on the semaphore. One is wait, the another one is signal. So these 2 are the operation. So this wait operation, it is also called as P operation. Okay, it is also called as P, or it is also called as sleep operation, or it is also called as down operation. So okay, this is down. Okay, so wait operation, it is also called as P, or sleep, or down operation. Then the signal operation, it is also called as V operation, or wake up operation. Sleep opposite is wake up, right? So it is wake up operation. Then opposite of down is up. It is also called as up operation. So both the operations are atomic, right? And your semaphore, it is always initialized to integer 1. So atomic operation means the variable on which you perform the read, modify and update, it happens at the same time with no preemption. That means in between your read, modify and update, no other operation is performed that may change the variable status. So whenever you have this semaphore, it is used to um, solve critical section problem and to achieve synchronization, right? So what will happen is like basically your critical section that would be surrounded by both of these operations, wait and signal. So it is something like this. Say suppose you have your critical section here. Okay, so this critical section would be surrounded by your wait operation. So say some code is there here. This is your wait operation. Then you have your critical section. Then you have signal operation. Signal of yes. Then you have your reminder section. Okay, maybe it is not visible. I will write here. So after signal you have reminder section. Okay. So this critical section, it has to be surrounded by your wait and signal operations so that you can solve the synchronization problem. Okay, so let's take an example and see how this helps in the mutual exclusion. Okay, like say suppose we have two process P1 and P2. There are two processes and they want to enter the critical section. Okay, and we have a semaphore, say yes. By default it would be initialized to 1. So whenever we had seen right just now, whenever a process it wants to execute its critical section, that would be surrounded by wait and signal. So say suppose your P1, say primarily your P1 and P2, they both are executing in their non-critical section. That means any other section apart from the your critical section, and S your semaphore by default it is 1. Now say suppose P1 it enters the critical section. Okay, your P1 it has entered critical section. That time what will happen? So first it has to your P1 has entered the critical section, means first wait operation would be executed, right? In the wait operation what do we have? It decrements the semaphore value. You can see here, right? While s is less than or equal to 0, no operation will be performed. If it is false, the s would be decremented by 1. So in our case, s becomes 0. Okay. First, s becomes 0, then P1 would be executing in its critical section. And say suppose P2, it is still executing in its non-critical section. Fine. So this is the case. Say in the third step, what will happen is like P1 it is still in its critical section. Your S semaphore is 0. Why? Because it is still P1 is executing, right? And say suppose now P2 it wants, okay, it wants to execute, I'll write here, it wants to execute its critical section. Now your process P2 has to wait unless and until P1 comes out of the critical section, and once it comes out of the critical section it has to execute this signal operation. Okay, so say suppose P1 already exited from your critical section. So it is exited from the critical section and it has it has also executed the signal operation. Whenever the signal operation it is executed, what will happen is you have a command over here s plus plus. That means your semaphore would be incremented by 1. So s will become again 1. So see here P2 when it wanted to execute the critical section it cannot execute. Why? Because it knows some process is executing in its critical section. How it knows is by this semaphore value. So whenever this value becomes greater than 1, then only P2 understands that now it can enter the critical section. So here S your semaphore has become 1 so that your P2 can now enter its critical section and it can start executing. So once it starts execution, what it has to do is like again the wait operation would be executed, and again your P2 semaphore value it becomes 0. So this is how it implements the mutual exclusion. So no need to remember these all things. This is just for your understanding purpose. So just remember that semaphore, it is an integer variable and it is shared between the threads, and it is a variable that is used to solve your synchronization problem and critical section problem. And again, these two operations are very important. So apart from initialization, your semaphore, it can be accessed only through wait and signal operation. So the different names for wait and wait and signal operation has been given here. Fine. Okay. So this is regarding your semaphores. That's it for today. We'll conclude our session. Thank you.